This is video 2 for the electrical safety unit notes. Now for this one, we're going to talk about how to make a safe circuit. And to begin, we have to talk about, circuit paths. We've already seen that electricity needs a path to follow continuously. That's usually a wire. Now this is why you get a jolt from static electricity. But it's a momentary thing. What happens is as you move around in the wintertime, charges build up on your body. And then when you touch something that's connected to the earth, the electrons jump from you to that thing and go back into the earth. So momentarily there is a path for the electricity to flow. However, with static electricity, it's a very, very fast thing. It does not take very long for those charges to flow from you back to the ground. And once it's done that, it's the electricity stops flowing, and this is why static shocks are rarely hazardous. They just don't last very long. So the way we get shocked is by providing a path for the charges to go to ground. And this is one reason why birds can sit on a power line. The electricity is not flowing through the bird to the ground. So let's take a look at this. Here we have a battery symbol where the long line represents positive and the short line means negative. So let's say up here this is like positive 10 volts and this is 0 volts. So our EMF is 10 volts. That means on this resistor, on this side, I'd have 10 volts, and on this side of the resistor, I would have 0 volts, and my delta V would be 10 volts, 10 minus 0. So let's take a look at what's happening with the bird. I'm going to do a cutout here, expand this out. So bigger here. So here's our wire. And we can think of the bird as a resistor. So here's one foot of the bird, here's the bird's body, and then here's the other foot of the bird. Now, with this electricity, first off, there's a couple reasons why the bird is safe. On this foot, I have 10 volts, but on this foot, I also have 10 volts. So the delta V equals 0. So that's one reason why the bird is safe. There's no potential difference drop across the feet. Another reason why it's safe is that electricity follows a path of least resistance. And there's less resistance for it to keep going through the wire than it would be for it to go up through the bird. So those are two reasons why that bird is safe. Another reason, electromotive force, EMF, or voltage, it motivates electrons to move through a conductor. Now, voltage is always relative between 2 points. The bird, in the previous example, was located at just 1 point. So even though the bird has 2 feet, both feet are touching the same wire, they're electrically common. That, that one foot is at 10 volts, the second foot's at 10 volts. So what does that mean? That means that you should be safe if you're grabbing a wire. And you'd be partially correct. So for example, say the positive terminal is at 10 volts, the negative terminal is at 0 volts. If I follow this up here, at this one part of your hand you have 10 volts. At the second part of your hand you have 10 volts. So delta V is 0. So you should be safe. And in fact, you would be. As this is set up, you would be safe. However, your feet are touching the ground. And let's say someone attached cable from the circuit to the ground. Now we do have a special symbol for this. We use 3 lines, each one shorter than the previous one. And if I do this, all of a sudden, now you have 10 volts up here, but you have 0 volts at your feet. And now there's a voltage drop of 10 volts between you and the ground. So if someone were to put in a ground, if someone were to ground this circuit by attaching a wire to the negative terminal of the battery and attaching it to the earth, that provides a path between you and the positive terminal of this battery, and you will get shocked. So let's take a look at some examples here. So in this first circuit right here, we have a circuit that's been grounded, and this is actually common. Most circuits are grounded. And if we take a look at this, let's say again we have 10 volts and 0 volts. If we take a look at this person here, they're attached at the bottom side right here, so that they have 0 volts. And notice that they're in line with the bottom wire with a negative terminal. This means that person is at common. They are electrically common. And notice that they have 0 volts up here. They have 0 volts at their foot. Delta V equals 0, so there's no motivation, and the person will be safe. If I look at this second example here, notice that there's no ground. And since there is no ground, even though this person is grounded, the person still will be safe because there is no path to connect this person to the negative terminal of this battery. So that person right there will be safe. Now, if I take a look at this next example, this is where it becomes really dangerous. It's accidental grounding. So let's say a tree grows up underneath a power supply, and it doesn't have to be a tree. It could be a piece of metal leaning against something. It can be a plant. It could be a branch. It could be anything. But let's say that a tree has accidentally grounded this circuit. Now, when this person touches it, at their foot they have 0 volts. At their hand they have 10 volts. Delta V equals 10 volts. There's now motivation, and this person will become shocked. They will get electrocuted. Let's say the tree touches the 10 volt side. Well, that changes things. Now this person on the top, at their hand they have 10 volts. At their foot they have 10 volts because the tree is attached to the positive terminal. So again, it's accidentally grounding, but for the top person above this circuit here, this resistor, their delta V equals 0, so they're safe. However, if a person were to touch below here, well, at their hand they have 0 volts, at their foot they have 10 volts, so delta V equals 10 volts. There's now motivation, and that person will get shocked. Okay, let's look at one final example. This circuit is not grounded. It has not been accidentally grounded, but we have 2 people touching the ground and touching the circuit. Both of these people will get shocked. Because this person on the bottom is touching the line right here, there's 0 volts at this point. There's 10 volts up here, and between the 2 of them, because they're connected through the earth, there's a potential of 10 volts for both of them. So both of these people will get shocked. All right, so looking at these circuits, I hope that you can see that a safe circuit design then would in fact have a ground placed in it. And you may be thinking, okay, well, if I have a ground in it, if I touch it on the bottom side, I'm safe, but if I touch it on the top side, I'm in danger. And you're right. If I compare circuits 1 and 3 here, if the circuit's grounded, if you touch it on the hot side, you're going to be electrocuted, but if you touch it on the cool side, you'll be fine. But we want that. Uh, it's like thinking about this way: 50% of the time, you're going to be safe. Um, and the last thing you want is to have it accidentally grounded, so that you have no idea, if you're going to be safe. You know, if we take a look at circuit number 2, if there's no ground on the circuit, yes, the person would be safe no matter where they touch this circuit. However, if it becomes accidentally grounded, like in circuit number 3, there's a chance for someone to get hurt. So it's always a good idea to ground your circuits. Or if it's a very simple circuit that you can see completely, you may not want to ground it, so that's safe all the way around. All right, that concludes this video.